Okay, in this video I want to practice actually finding a Fourier series for a given function. So I'm given this piecewise function, which is 0 from minus pi to 0 and pi minus x from 0 to pi. So our domain is the open interval from minus pi to pi. And if you look back at the previous video, we're going to assume that our domain is from minus p to p. And so this is telling us that p is equal to pi and minus p is equal to minus pi. Okay, so what that means is when I plug into our formula for a0, which is 1 over p definite integral minus b to p f of x dx, all the p's are going to be pi. And the f of x is this function. And so right away that means that we're going to have to split it into two integrals, an integral from minus pi to 0 and an integral from 0 to pi. So 1 over p is equal to 1 over pi. And then we split our integral into two pieces, an integral from minus pi to 0 plus an integral from 0 to pi. On minus pi to 0, our function f of x is equal to 0. So f of x dx would be 0 dx. And on 0 to pi, f of x is pi minus x. So we would have pi minus x dx. Okay, integral of 0 is just going to be 0. I'm not even going to do that one. This one, integral of pi, is going to be pi x. Integral of x is minus 1/2 x squared. And then we're going to evaluate from 0 to pi. And so if we plug in our limits of integration, we get 1 over pi. Top limit would be pi squared minus 1/2 pi squared. Bottom limit of integration would give us 0 minus 0. And so we really just have pi squared minus 1/2 of pi squared, which is 1/2 of pi squared. And so we get 1 over pi times 1/2 pi squared. And if we cancel a pi, we get pi over 2. So our a0 is equal to pi over 2. We also need to find an, and I'm not going to find these individually. I'm going to find all of them at once. I'm just going to leave n as a variable. Our formula was 1 over p, definite integral from minus p to p, f of x times cosine n pi x over p. I'm going to plug in p is equal to pi. So we have 1 over pi, definite integral minus pi to pi, f of x cosine n pi x over p, which is pi dx. And conveniently we have a pi canceling, so we really have cosine nx, which is much simpler. Yeah, honestly the most common p's we're going to see are the number 1, p is 1, or p is pi. Okay, anyway, f of x is piecewise, so we're going to have to split this into two integrals. So we'll have 1 over pi, integral from minus pi to 0, in which case f of x is 0. And definite integral from 0 to pi, in which case f of x is pi minus x. Okay, first integral again is integral of a 0, so we don't have to worry about that one. Second one is going to be a little trickier. We're going to have to distribute this and make it pi cosine nx minus x cosine nx. I'm going to just go ahead and show you all the details. This one is going to be a u sub with u is equal to nx, so we're going to end up dividing by n. So let's see, we'll have pi over n sine nx. If you double check, the derivative of this function would be pi over n cosine nx times n. The n's would cancel, pi cosine nx. Over here, I think I'm going to do integration by parts with u is equal to x and dv is cosine nx, which means du is dx and v is 1 over n sine nx. So uv minus integral of v du would be x over n sine nx minus the integral of 1 over n sine nx. Let's see, integral of 1 over n sine nx is 1 over n squared cosine nx, and we're going to flip the signs. Okay, so all of this is the integral of x cosine nx. So we should end up with minus x over n sine nx plus 1 over n squared cosine nx. Okay, let me pause the video and double check my work. Okay, coming back from pause, I see one error I made. This is a definite integral, so I need my limits from 0 to pi. And one other thing that isn't wrong, but I could have maybe done better, I probably should have just done integration by parts from this step, like let this be my u and this be my dv, and then I don't have to split up and do two separate integrals. But oh well, I've come this far. So let's continue. Let's plug in our limits of integration. If we plug in pi, we have pi over n sine n pi minus pi over n sine n pi. Distribute the minus 1 over n squared cosine n pi. All that was plugging in pi. If we plug in 0, we get pi over n sine of 0 minus 0 over n sine of 0. Distribute the minus 1 over n squared cosine of 0. Okay, plus side, we have a lot of zeros. Sine of a multiple of pi, that's a 0. Sine of a multiple of pi, also a 0. Also the two cancel each other. Let's see, sine of 0 is 0. Sine of 0 is 0. So really we're just left with these two things, and you'll notice that cosine of 0 is 1, and cosine of a multiple of pi is going to depend on which multiple it is. If n is an even number, you're going to get 1. If n is odd, you're going to get minus 1. So an easier way to write cosine n pi is actually as minus 1 to the n. If n is an integer, these two things are the same. So that's just a nifty way to rewrite it. You could probably just leave it as cosine n pi if you're worried about it. So anyway, we have 1 over pi. Let's see, minus minus, this 1 would be positive. And minus this guy, which I think I'm going to rewrite as 1 minus alternating sign with the pi and the n squared both in the denominator. Okay, let's pause and get a new piece of paper. Okay, coming back, we've found a0 and an. We still need to find bn, which is going to be defined the same way. It's an integral of f of x times sine instead of cosine. And then we plug in our p is equal to pi, and our f of x is a piecewise, so we have 1 over pi, integral from minus pi to 0, 0 times sine nx, since the pi and the p are both going to cancel. And from 0 to pi, our function f of x was pi minus x. And then we have sine of nx dx. I'm just going to put dot, dot, dot. This video has gone on long enough, and the integration here is going to be very similar to the integration we just did. the answer you should end up with is much simpler in this case. It actually has so much cancellation and ends up working out to 1 over n. Okay, so anyway, our punchline, once we've found the 3 sets of constants, the a0, the an, and the bn, then we can actually plug in our formula for the Fourier series. And so the formula for Fourier series was a0 over 2 plus a sum from 1 to infinity an cosine n pi x over p plus bn sine n pi x over p. Okay, I'm going to slide up. And so now we know all these constants. So a0 was pi over 2. So our numerator is pi over 2 plus a sum from n equals 1 to infinity. I'll put brackets around that just so we keep track of what's actually inside the summation. An was wonky constant. 1 minus alternating sine over pi n squared multiplied by cosine, let's see, n pi x over p was actually just nx. And bn was 1 over n. And again, sine n pi x over p was just sine nx. So you're going to be seeing the same inside angle over and over again, the same sines and cosines over and over again. So this is actually the Fourier series. The only thing I could do to rewrite this to make it simpler is maybe just call that pi over 4. Nothing else is really going to look any different than what you see written in front of you. Okay, so that is our example of a Fourier series, and this is our answer for the Fourier series. The next video is actually just going to be a description of what the graph is going to look like.